Good morning, class. I'm still getting some technical stuff set up, so I'll start in a few seconds. All right, let's get started. I think the YouTube streaming's finally managed to work, so um, let me verify that one more time. And while that's happening, let's get going with today's lecture. Um, we are now, I think, roughly in the final month of the semester, and um, as always, around this time, I'm scrambling for time, which even though this is a strange semester by many measures, I think this one thing has not changed. So a few announcements. Homework 2 is still being graded. We should get back to you, or should be done sometime soon. I'm hoping by this weekend. And there will be another homework 5, which will be available on Canvas. Now, this is going to be a slightly different homework. It's going to be due in 1 week. It will be essentially a Canvas quiz style homework. So you just get a week, you get 2 attempts and all that. What the homework will entail is it will require you to watch a lecture on ensembles and boosting. And the whole homework is essentially a set of questions that will guide you through understanding that process. So you'll get 2 attempts at that homework. Now, once that homework is done, after that, we'll get to the homework on SVMs. Are there any questions? Okay, there was a question about the homework on SVMs. Yes, that'll happen after the one on what do you call it? Boosting. Any other questions? Looks like there aren't. Another set of reminders. So there is a project milestone 2 that's approaching on Canvas. It requires 2 more submissions. Remember, by the end of the semester, you'll need 6. For project milestone 1, you already had 1. For 2, you'll need 2, and for the third one, you'll just need 3 more. In addition, just to make sure that um, the thing on Canvas also sees an entry, I want you to write a very short report on Canvas. Submit a short report in addition to those 2 submissions on this is 2 more submissions to Kaggle. Yeah, in addition to the 2 Kaggle submissions, I want you to submit a short report that describes what you've done since the last milestone. For example, you used a new feature set or something like that. Any problems that you may have faced along the way, and what's your plan for the rest of the semester? What do you plan to do with respect to what kinds of things you want to try or and so on. Just to kind of help you plan that, remember that you will for the next homework, you'll be implementing SVM. And if the timing is right, I'm still kind of working on this. If the timing is right, also logistic regression for that homework. And then we'll also have, um, you are allowed to use a third-party library for the thing. You can, for example, one of your 2 submissions could be um, for this upcoming milestone could even be a third-party library if you want to use it. Just think about how you plan to set things up for the rest of the semester. Just as okay, there are a couple of questions. We've only implemented 2 algorithms with the milestone. So while with the milestone we need 3 total submissions, it looked like ID3 was taking a hours to run on the data set. So do you have recommendations? Yes. So remember, you need 3 submissions. You can, in theory, use 2 different feature sets for with the same algorithm. So let me just enumerate the different algorithms that we've seen so far. We've seen ID3, we've seen perceptron, we've seen SVM. And as part of this week's homework for the lecture that we'll see, you will encounter this really powerful idea called ensembling, which allows you to essentially plug and play other classifiers to create. Ensembling is this meta algorithm that allows you to construct classifiers using other classifiers as pieces. So you can kind of plug and play things. And in terms of features, you have bag of words, you have glove, and you have TF, IDF. And then you also have an extra source of features, which I'm calling the miscellaneous things, like gender and other attributes that are available. So for this submission, for example, you could mix and match these things. You could, for example, mix perceptron with bag of words and perceptron with glove just to see how it goes. And ID3, as Ben pointed out, ID3, if you use it with, say, bag of words or TF-IDF, it's going to take a lot of time because there are 10,000 features. So you might have to discretize things. You might have to discretize each feature so that the number of branches is small, or you might have to discretize the entire feature set somehow by constructing, say, by using ideas from the ensembling lecture, or you could connect ID3 to miscellaneous. You could invent features from the miscellaneous set, and that will what will the number of miscellaneous features is small. And I know that some of the top submissions on Kaggle right now do use miscellaneous and pretty much entirely just that. So you could do that also. Another option that you have is external library, and for this you can play with sklearn or PyTorch, or pick there's TensorFlow. For example, you could use the random forest implementation or the boosting implementation from sklearn to see how things go. So any of these things are okay. So you have more than two more options to play with. So the total number of submissions, to answer Anthony's question, the dummy submission, I'm not even counting it. So yes, if you include that, there should be 4 at least. You can also use an ML library and so on. So does this hopefully answer your question, Ben? I see that there's a part of your question that I did not answer, which is ID3 takes hours on the data set. So yes, ID3 might end up taking hours if you use bag of words or TF-IDF, simply because it's there are a few things that you could do. One of those is one possible reason it might be going slow is because, remember, for bag of words especially, even though the features look like they are integers, you should treat them as real numbers, and then you need to bucket them into some reasonable categories. So think about bucketing. You could, for example, without looking at the data, you can just pick a certain threshold and say, if the feature value is more than the threshold, it's one bucket, otherwise it's the other bucket. And this binarizes the entire data set. That will reduce some amount of computation that you do. Another thing that you could do is, as I said, just use the miscellaneous features. A common mistake that, not a mistake, but a common inefficiency that ends up in a lot of ID3 implementations that you've not thought about it is in the innermost loop of ID3, you're picking the best feature, which is for that you're computing the information gain. The information gain of a feature, let's call that A, and a data set S, is the entropy of the data set minus the sum over A in A of something. Notice that this term doesn't depend on A, so you don't need to recompute that all the time. So you can compute that before entering the loop over all the attributes, and this will save some time. Another thing to note is that this information gain itself for a particular feature does not interact with any other feature, so you can parallelize this. So if you have a multi-core machine, you can use many cores to do this work a little faster. So these kinds of tricks tend to help. All right. So there's another announcement I have, which will also be posted on Canvas after the class. Many of you, or at least several of you, suggested to me that I should incentivize the Kaggle game a little more. I mentioned before that your standing on Kaggle is not going to matter for your grade, and I still maintain that if I'm not going to take away points just because uh, one of your submissions is not doing well, provided the rest of the class also gets similar accuracies for that kind of a submission. However, to incentivize you to get to the top of the leaderboard, I'm going to offer an extra credit essentially. The top 10 students on the private leaderboard on Kaggle will get half a letter grade bump. So if you were getting an A minus, you'll be bumped up to an A B will become a B plus, and so on. And this is only for the top 10 students on, importantly, the private leaderboard. You get to see the public leaderboard. I get to see the private leaderboard. Your examples that you submit are partitioned into two, and even I don't know how the partition happens. Kaggle does that. And even though you are ranked in your view, Kaggle in the leaderboard, you're ranked according to the public leaderboard. The ranking that I see is both the public and the private leaderboard. And since the whole game of machine learning is generalization, I'm going to use the private leaderboard for deciding who gets the letter grade upgrade. And I think when I checked last, the list of students at the top 10 of both the leaderboards is the same. So I don't think that's too much of a concern, or maybe that's like, I think it's basically the same. So there will be an announcement about this on Canvas also. This is just to incentivize you to, to kind of try to get to the top of the leaderboard. Any questions? How about number one? I don't want to separate out number one and two simply because they're all going to be really close to each other at the end. So it's instead of the top one, it's the top 10. As far as I'm concerned, anyone in the top 10 are essentially very similar to each other. Other questions? Either you're all stunned about this announcement, or you really don't care, or there are no questions. Unfortunately, because I can't see your faces, I can't tell the difference. Stroked is a good thing, yes. So I'm going to assume that there are no questions and carry on with our lecture. So today, we're going to see two important concepts, or at least we'll see one concept once again, which is very important. And this will be an important idea, especially when we talk about logistic regression and neural networks and such things. Oh, there's a question. Will only the top 10 count for the code we write, excluding library submissions? No, I'm going to actually allow top 10 among the 6 official submissions, any of the 6 official submissions. For example, if you decide to submit 20 things with library submissions, I'm going to take only one of them. You're free to submit more than 6, of course, but I'll take at the end of the semester, you will decide on which 6 things count as your official runs, and I'll only take those 6 and the top 10 according to those things. This is a little bit more work for me, but that's okay. I'm going to include library submissions in this thing. All right, so we're going to look at this idea of learning as loss minimization. We've already seen this before. And I just want to kind of put this in perspective so that you have this information in one place. So the general idea for treating learning as loss minimization looks like this. We have a set of examples, X, which are drawn from a fixed and unknown distribution, or perhaps unknown distribution. And there is this Oracle classifier that labels examples. We don't know what this function is. This is a function that we wish to mimic. So our goal is to find a hypothesis, H, that mimics this function, F. In order to do that, we have thought about various different approaches for learning. And here's a general scheme that unifies many of these ideas. In the ideal case, what we will do is we'll define a function L that penalizes bad hypotheses. L is a function, you can think of L as a function that operates on, um, that takes, say, ground truth and prediction by some hypothesis for a certain example. So we want to think of this as, for example, mistake. L is a function that can either it gives a zero, it gives a penalty of 0 if the ground truth is identical to the prediction, or it gives a penalty of 1 if there's a mistake. So this is just, it's called a loss function. The goal of learning, if you have such a function, is to pick a hypothesis, pick a certain hypothesis among the entire hypothesis space that minimizes the expected loss. So expected loss is a concrete term. What we want is to find a certain function h that minimizes this loss function, but actually the expectation of the loss function, and the expectation is taken over this distribution over examples. So examples are drawn from this fixed and unknown distribution, and you compute the loss on all of these. And essentially, if you're doing this, and if you knew this distribution, you could just compute this value L for each example or sample from that, and enumerate every possible hypothesis if computationally feasible, and find the one that has the lowest expected loss. Unfortunately, this is a problem because we don't know the distribution. The distribution D is unknown. So we need to somehow figure out how to get around that problem. The answer is we have a training set. The training set is simply a set of examples that are drawn from this distribution. It's a finite set of examples of M examples that are drawn from this fixed and unknown distribution. And we want to compute this expectation. And instead of computing the expectation, we will take the empirical average of all the losses. This empirical average of all the losses, which is simply summing over all the losses and dividing by the number of examples that we have, is called the empirical loss. So instead of, our goal is to minimize the expected loss, which we can't do because we don't know the distribution over examples. But we do have a sample of examples from the distribution, and we're going to take the empirical average and we can minimize that function. This is the agenda for learning as loss minimization. Unfortunately, I'm going to argue that there's a problem here. Can someone find a problem? And you can type it out on chat. What could go wrong if you find an example, find a classifier that achieves 0 loss, or a perfect classifier on the training set? And yes, there's an answer in the chat. This may overfit. You could easily find a classifier. So I let me give you a classifier that gets perfect accuracy or 0 loss on the training set. What you do is I put the entire training set into a database, and when a new example comes in, if it comes from the training set, I will look up that example in the database and return the label. If it does not belong to the training set, if it does not show up in the database, I'll just return a random label. So for any example in the training set, it will get the perfect label. Of course, it's not learned anything. So that's an extreme overfitting classifier. So we need to somehow influence this search over classifiers, this minimization of loss, to prefer classifiers that don't overfit. And using the intuition that we've seen in Occam's razor, we want something that biases this search towards simplicity, towards a simpler hypothesis. This is done using something called a regularizer. A regularizer is an expression, a function of, you can write this as, I'll write this below. You can write this as a regularizer can be thought of as a function that takes a hypothesis and produces a number. And this number is larger for more complex hypotheses. So we can introduce a regularizer, and this gives us the idea of, instead of just loss minimization, it gives us regularized loss minimization. So the full name is really regularized empirical loss minimization. What we have is, we have two terms here. We have a regularizer and the average, the empirical loss or the average loss. And we want to somehow minimize both these things. So we just add them up and add the scaling factor C that combines the two of them. And our goal of learning is now to search over all hypotheses and find the one that has the lowest sum of the regularizer plus empirical loss. So we still have this thing. We still have the minimization over the hypothesis. There's an interesting question here. What happens if F is really complex? What happens if the true classifier, the true function, is actually a complex function, where complex or complicated function? It's not a simple function. What that means is that if F is really complicated, then this second term ends up being high for functions that are not simple. Even though the regularizer might be small for simple functions, the empirical loss might end up being high. And the hope is, if the C is well chosen, even though the regularizer will get overruled by the empirical loss. So really, we have these two things. The regularizer prefers simplicity, and the second term, the empirical loss, allows complex hypothesis. And what this minimization is saying is, I want only as much complexity as is needed and not more. And even if the true function is really, really complex, if I can find a simple classifier that is nearly as good, I would rather prefer that. So this 1 over m term here is just, you have m examples. So the number of examples is m, so this goes from 1 to m, and so this makes it the average. So you add up the total loss and divide by m, the number of examples, you get the average loss. Technically, it's just a constant. It could be absorbed into the C, and that's what we do effectively for support vector machines, for example. With linear classifiers, this particular hypothesis is defined, is completely identified by a weight vector. So h of x is the sign of the weight times the input. So the one regularizer we have seen already is this one. This is the squared norm regularizer. And we've already seen why this is an interesting thing. It essentially makes the margin larger, and that's a good thing, because larger margin is it corresponds to essentially, in a certain manner of speaking, simpler classifiers, because the VC dimension is lower. The second term, the loss, instead of I have rewritten this h this function instead of in the original case, I had loss of prediction and the ground truth. I moved the ground truth here, and I have given both the example and the weights. Using them, you can construct the prediction using this rule. So the loss is a function of the true label yi, the example xi, and the weight vector w. So we've already essentially we have seen a version of this, but I want you to think about this outside of this SVM kind of scenario more generally. Notice that I have committed to the SVM style regularizer here, but I have still left this as an abstract function L. We can pick any loss function. Who says that we should use only the hinge loss? Loss functions should penalize mistakes. We are minimizing the average loss over the training data. So if the loss function keeps increasing the mistakes increasing as the number of mistakes grows, the question to think about is what's the ideal loss function for classification? What would be a good loss function for classification? And you can again use the chat, partly because this is a question that's slightly more, it's harder to make into a poll. Remember, the thing that we want to minimize is mistakes. A perfect loss function could be exactly. There's a suggestion. The simple approach is a perfect loss function. The ideal loss function is simply the number of mistakes. Remember, I want to penalize mistakes. So the perfect loss function could be just literally the number of mistakes, or actually instead of number of mistakes, this is this is for a single example. So the loss function could be, did the classifier make a mistake on this example or not? So if you add them all, if you add those individual mistakes up, you get the number of mistakes. So this particular loss function, which is in some sense exactly solving the question that we want to address, which is the number of penalizing the number of mistakes, is called the 0-1 loss. The 0-1 loss for an example for any particular example is defined to be 1 if the prediction and the ground truth are different, and 0 otherwise. Basically, think of it as this is the number of points that gets taken away for a certain y and y prime. If y is the prediction, I can't remember the order anymore. If y is the prediction and y prime is the ground truth, or vice versa, it doesn't really matter because it's symmetric. So think of this as how many points get taken away for this one example? Well, if there's a mistake, 1 point gets taken away. If there's no mistake, no points get taken away. And you add this number of points taken away over the entire data set, you get the number of mistakes. If you want to ground this in the context of linear classifiers, you have the prediction y prime is the sign. So the mistake happens when y w transpose x is negative. So I can rewrite this. This is a mistake. So this is L01 of y, comma, x, and w. So L01 of y, which is a 0-1 loss for a particular example xy, and the weight vector w is 1 if yw transpose x is negative, otherwise it's 0. Essentially, these things are the same. So basically, you lose a point, the classifier loses a point if it makes a mistake. And the loss for the data set is the number of points it loses. So notice that, interestingly, this 0-1 loss for a binary classifier, for a linear classifier, is a function of y times w transpose x. If that quantity is negative, it loses a point. If that quantity is positive, it gains a point. It doesn't lose anything. So minimizing 0-1 loss, unfortunately, is an intractable problem. It's a computationally intractable problem. So we need surrogates. If you want a pictorial representation of this, so by the way, before we talk about pictorial representations, are there any questions about this agenda, about this notion of minimizing loss and about this 0-1 loss? The 0-1 loss, I think, is a rather unimaginative name for the function. There is no assumption of linear separability here. It's possible that maybe the loss is never going to be 0. Maybe who said that this quantity has to be 0? Maybe that quantity never becomes 0 because the data set is not linearly separable. For a particular example, notice that this expression here is for one particular example. So it just tries to find how many, did this particular example make a mistake or not? There's another question. Minimizing the regularizer, that's this expression here, just seems to decrease the length of the weight vector. Why does this increase the margin? This is something that we've spoken about when we talked about SVM. remember that the margin is, the way this is set up is the margin is a function of 1 over the norm of W. So as the length of the weight vector becomes smaller, the margin becomes larger. And I'm going to refer you to the discussion that we had with the SVM lecture to revisit that point. Other questions? We have really not solved anything so far. We have just taken what we have seen and reframed it using a certain language, reframed it using this language of loss minimization. It's just a convenient abstraction, and I think a very useful generalization, because it's going to give us the technical or the conceptual tool for defining any sort of a classifier, because it doesn't matter what learning, what hypothesis space you use, you can always define a certain loss function and define a certain regularizer and work with that. Other questions? Is there a graphical way to visualize this? That's a fantastic segue. So remember that this function here, the loss function, is at least for linear classifiers, and more generally for any classifier where you make the prediction as sign of some score of an example. Here score is y, just W transpose X. To any classifier where you make a prediction in this way, I can write the loss as y times, in terms of y times score of X. If y times the score of X is negative, then the loss is -1. So we can think of the loss as a function of the score. So it is y times W transpose X. We can think of the loss as a function of y W transpose X. And that's where this graphical thing shows up. So the horizontal axis here is y W transpose X, and the vertical axis is the loss. Remember, when y W transpose X is positive, both y and W transpose X, the score for that example, are the same sign. If they have the same sign, there should be no loss. So if y W transpose X is positive, and doesn't matter how far it becomes positive or how close it becomes to 0, as long as it's positive, the number of points that this particular classifier, which is completely defined by W, the number of points it loses is 0. If, on the other hand, y W transpose X is negative, we are on this side, then either y is positive and W transpose X is negative, or y is negative and W transpose X is positive. Either way, they disagree, which means there has to be a point taken away. So the 0, 1 loss becomes 1 on the negative side of this plane, on the negative in this side. So why is the 0, 1 loss intractable? There are many answers for that. One simple answer is, notice that at this point, this is not really a continuous function. At 0, there's an abrupt jump from 0 to 1. So we don't have a continuous function. We can't use any gradient-based methods. It's essentially a combinatorial search. So this is the problem. How do we get around this thing? The answer is we can't deal with this function. So we invent surrogates. We create other functions that have similar properties. In addition to having similar properties, we also want them to have nice optimization properties. In particular, we would like it to be convex. One convex function that we have already seen that is essentially envelopes the 0, 1 loss is the hinge loss. This is what the SVM classifier is defined by. What it does is, if y W transpose X is more than 0, in fact, if it's more than 1, then it is no loss. If y W transpose X is between 0 and 1, that means the prediction is correct, but the example, the score, the y W transpose X is too close to the margin. So you have a loss which is 1 minus y W transpose X. And if it's on the negative side, it's incorrectly predicted. So there is still a loss, there's still a penalty on this weight vector, which is equal to 1 minus y W transpose X. Oh. And so the other thing is the penalty keeps increasing as the point gets more and more on the wrong side. The penalty also keeps increasing, and the goal of learning is to find a weight vector that takes you down this thing, and preferably on the side. So the goal of learning with hinge loss is to find a classifier that puts you on anywhere on this side of the line. With hinge loss, we are essentially saying anywhere on this side is good. So this is a surrogate. There are other surrogates for the 0-1 loss. We've already encountered this surrogate. The support vector machine is simply another way to, a perfectly reasonable way to introduce support vector machines is to say, I'm going to operate in this world of empirical risk minimization, regularized empirical risk minimization. And for that, I'm going to use the regularizer that I'm going to use is this one, the half W transpose W. It's the squared norm regularizer. The classifier that I'll use is a linear classifier, and the loss that I will use is a hinge loss. So the SVM minimizes the hinge loss plus the squared norm regularizer. This is I mean, if we are willing to live within this world of regularized risk minimization or loss minimization, then we can think of an SVM as just a classifier that's just a linear classifier that's trained by minimizing the squared loss, the squared norm regularizer plus the empirical hinge loss. This is it. If you change one of these things, you get a different learning algorithm. If you change the hinge loss to something else, you get a different learning algorithm. If you change the regularizer, you don't call it a different learning algorithm. You have other kinds of regularizers. You just name it. You say, for example, the L1 regularization gives you the L1 SVM and so on. So this is once again, so far we have seen nothing new. It's just a different perspective on the same idea. And this will now become a common theme for the rest of the semester. We will see essentially ideas that we have encountered, except using a different lens. And suddenly, by looking at it through a different lens, it gives us other kind of things that we can change. I could have changed the regularizer and I get a different thing. I could have changed the loss function. I get a different classifier. So there are many variants. This is just a way of inventing learning algorithms if you want. Just to kind of tease apart the various parts of the SVM, we've already encountered this. This term, the first term is the regularizer. The second term is the empirical loss. For the SVM, the regularizer says, I prefer classifiers. I prefer weight vectors that maximize the margin. And among all classifiers that are roughly the same, it imposes a preference over the hypothesis space by going for better generalization. This term can be replaced with such other terms that serve a similar purpose. In the loss side of things, you have the hinge loss. It penalizes weight vectors that make mistakes, or it also penalizes weight vectors that puts examples too close to the margin. It can be replaced with other loss functions that impose other preferences. Between these two, governing the importance of these two things, or in some sense, balancing these two things, is a hyperparameter C that controls this preference between a larger margin and a smaller loss. Are there any questions about this? Are there any questions about this perspective on support vector machines? Notice that I have completely sidestepped an important question. I basically said we're going to learn by minimizing the empirical loss by setting up an optimization problem that may look like this, or like this. I didn't talk about how this optimization problem is going to get solved. You can solve this optimization problem using any optimizer. In fact, that's like one of the big successes in applied machine learning today. we have separated the problem, the question of how do I define a classifier as a good or bad one. That's what we're talking about now. I define a classifier to be good if it has a lower regularized empirical loss. I've separated that concern from how am I going to actually find a classifier that's good. To find a classifier that's good, I can use any optimizer. We have looked at stochastic gradient descent, but there are variants of that. There are other algorithms. There are very good libraries. One perspective on the state-of-the-art machine learning libraries out there, say, for example, PyTorch or TensorFlow, is they're really fantastic optimization libraries that use a certain kind of, that use essentially gradient-based optimization. And they do that really, really well. And the whole problem for whole goal of learning is now changed into how do I invent a learning algorithm to how do I invent a loss function and a regularizer for some classifier that I have, and then give it to an off-the-shelf optimizer. There are many such optimizers. We've seen SGD, but there are other named optimizers. Adam's an example of that, and today Adam's the most popular one, which involves a little more technical detail. But there are, essentially what we are doing is it's another optimizer that comes with its own hyperparameters, and it seems to be fairly good for complicated functions like neural networks. Okay, but like I said, with SVM, you're making some choices here for the hinge loss and the regularizer, but we can make other choices. In particular, I want to spend a few minutes talking about other choices for this position here. I could use the hinge loss, and if I use the hinge loss, I get a SVM. Instead, it turns out there are many loss functions. Turns out if the perceptron algorithm that we've seen and you've implemented and so on is essentially, from in this perspective, the perceptron algorithm is just minimizing something called the empirical perceptron loss. The perceptron loss looks very much like the hinge loss, except it doesn't have that, just to kind of highlight the difference, it doesn't have that one there. The other thing that the perceptron does not have is it does not have a regularizer. In your homework 5 that will be released later today, I'll be describing something called the AdaBoost algorithm. I'll describe the AdaBoost in a very different way from loss minimization, but I'm just telling you now that it turns out the AdaBoost algorithm minimizes something called the exponential loss that looks like this. We will see logistic regression maybe, I think, next week, hopefully Thursday. And it turns out the logistic regression fits in the same framework, and we will see that this in a lot more detail. Logistic regression is just a linear classifier that minimizes what's called the log loss or the logistic loss. It's just another loss function. These are all different ways of saying this classifier made a mistake. If you want a pictorial version, here's all these losses on the same slide. Let me walk you through these. We have the 0-1 loss. The 0-1 loss is this step function. We've already seen the hinge loss. The hinge loss is max of 0, 1 minus YW transpose X. 1 minus YW transpose X applies on this side, and 0 applies on this side. So that's the hinge loss. That's the blue line there. The perceptron loss is essentially identical to the hinge loss, except the whole thing is shifted to the origin. So you don't have, that's why you don't have the 1 there. So and then there is another function. There's the exponential loss. The exponential loss is what the AdaBoost algorithm minimizes. And then the logistic regression classifier minimizes the log loss. These are just different surrogates for the 0-1 loss, because the 0-1 loss is intractable. Okay, let me briefly stop here for questions, because this is a lot of information. So if the 0-1 loss is the ideal case, how come none of these functions look like the 0-1 loss? That's an interesting question. Yeah, 0-1 loss is ideal, but none of them look like it, because when we are inventing loss functions, for historical reasons, I guess, we want the loss function to have a few properties. The first one is, in general, in terms of as a function of this is on this side, it's YW transpose X. In general, as YW transpose X goes towards that direction, we want the loss to decrease. In general, as YW transpose X goes in this direction, we want the loss to increase. So all these functions satisfy that property. The other property that all these functions satisfy, and this becomes an important one if you because of optimization concerns, is we want the loss to be convex, and all these functions are convex. The 0, 1 loss is not a convex function. So in fact, even if you try to approximate the 0, 1 loss with some other thing like a sigmoid, you won't get a convex function. So learning becomes a little bit more unstable. A third aspect here is, even though the 0, 1 loss is ideal, all these losses have a property that's very, very useful. As the prediction becomes worse, as the prediction becomes worse means YW transpose X is more and more negative. This loss becomes really large. All these losses become really large. And that means terrible classifiers, really, really bad classifiers are penalized very, very heavily. And that forces the learner to really prefer this region. So the 0, 1 loss, despite its simplicity in terms of explanation, has this really awful property in that a classifier that puts an example here and another classifier that puts an example here are essentially identical according to 0, 1 loss. They both lose 1 point. All the other loss functions that we have impose higher penalties as the prediction gets worse. And that's the reason why none of these functions look like the 0, 1 loss. The next question is, in SVM, we assume that the distance from the nearest point and the margin is 1 and continued with this assumption. When we use the SVM, we just initialize the weights and assume that this assumption is held, although the shortest distance of 1 might not be true with respect to the examples. That is true. However, the shortest distance of 1 will be true for all examples that are on the correct side of the margin. And you can actually empirically verify that. Except we don't know from the weight vector which examples, just looking at the weight vector, we can't tell which examples are within the margin or not. For that, we would have to go to a different representation, which unfortunately we are not going to cover this semester, it seems, because of time concerns. You need to go to a different representation of the SVM optimization problem called the dual representation. The dual representation essentially keeps track of which examples lie on the margin, which examples lie within, and so on. And looking at the dual representation for SVM, we will basically get, you can show that the property that Sevda, you mentioned still holds. Now the question, doesn't this make all the loss functions super sensitive to outliers? Yes, and that's why we have this regularizer that takes care of that. It still prevents, so one way of thinking about outliers is outliers are, being sensitive to outliers is what is the harm that's caused by overfitting. And if you have a regularizer in place, that problem gets taken care of. All of these are good questions. While you're thinking of more questions, let me kind of revisit or kind of summarize what we've seen today, what we've seen so far. This is, I've introduced this agenda of learning by loss minimization. Essentially, what we do is we don't want to invent learning algorithms anymore from this perspective. Instead, what we would like to do is we want to invent loss functions. We would write down a loss function. The way to learn is you write down a loss function, set up an empirical loss that needs to be optimized, give it to an optimizer, except you somehow need to account for the fact that you don't want to overfit. You can either regularize it, like we've seen here, or you can have something that some other thing that brings in generalization. In perceptron, the thing that brings in generalization is not a regularizer because perceptron does not use a regularizer. The thing that brings in generalization is averaging. Neural networks, in most of the time these days, I'm not entirely sure why, use something called dropout, in a similar sort of a procedural regularization. Essentially, dropout is a strategy that prevents overfitting. We'll see dropout maybe in 2 or something weeks. This idea is widely applicable. There are many different loss functions. All the examples that we've seen today are loss functions for classification. For regression, the loss function that's most commonly used is really the squared loss, or the squared mean square error that we have seen with least mean squares regression. There are many different loss functions. There are many different regularizers. If you're using a classifier, you can use one of these loss functions. If you want a multi-class classifier, the loss function that's used is called cross entropy. That's used for multi-class classification. For regression, the loss function that's used is mean square error. So essentially, you can now think of how the whole program gets mechanized. You pick a loss function, but you don't have to invent one. Somebody else has done the invention. If you're doing a binary classifier, you pick one of these loss functions. Most of the time these days, the most common loss functions are either hinge or logistic regression. If you're using multi-class, you use cross entropy loss function. If your problem is regression, you use a squared mean square error or squared error loss. And then you pick a regularizer. Either you write down a regularizer like what we have for SVM, or you choose to use a procedural regularizer like dropout, and you give it to an off-the-shelf optimization function, and we are good to go. Basically, you have invented a new learning algorithm. You may not even know what that learning algorithm is, because it's the optimizer that is actually doing the learning. So it's just, we've essentially, this is a strategy for mechanizing learning. So there's a question, why is cross entropy only used for multi-class classification? Isn't there binary class entropy? Yes, there is cross entropy. There is binary cross entropy. It's just that it has a different name. It's called logistic regression. Cross entropy is just the multi-class extension for logistic regression. All right, so are there any questions? What I've presented today includes material that we haven't yet covered. We'll talk in a lot more detail about logistic regression, but I wanted to present this because this is an important unifying idea, and we have really seen this idea at least twice so far. When we talked about least mean squares regression, we've talked about SVMs, and it turns out you've already seen the optimization aspect multiple times so far. We saw that with least mean squares. We've seen that with SVM, and even though I didn't present it as an optimizer, perceptrons also and a stochastic gradient descent, and so this is like a clean unification of a bunch of ideas. Are there any questions? Why call it cross entropy? That's for a different lecture. We'll get there. Eventually, it has interesting connections to information theory in its intellectual lineage. You could have just called it multi-class logistic regression, and it's basically the same thing. The loss function is easy to understand. What is the regularizer? This is the clever part. This is the complicated part. So let me revisit this thing alone. The loss function is just penalizing mistakes. If this is all there was, there would be overfitting. A regularizer is just a function. A regularizer is a function that takes a classifier and produces a number. It doesn't depend on any data. It's a function that essentially ranks classifiers by how simple or how complex the classifier is. So it's a measure, a regular, and if you're trying more complex classifiers end up having a larger value of regularizer. So the example that we've seen is this one here. Let me erase all this stuff. So the regularizer is a way of penalizing complexity. So more complex classifiers have larger values of regularization. So since we are minimizing, it makes sense to have defined the regularizer that way. One example of a regularizer that we've seen is this squared norm regularizer. This is, or I'm not going to write squared norm, it's just called the L2 regularizer. L2 because it uses the squared, the 2 norm, if that makes sense. But there are other regularizers. In some sense, regularization is just the idea that you want to somehow smooth out the hypothesis, the search over the hypothesis space, so that you don't automatically gravitate towards that classifier that perfectly explains the training set. So if this term was not there, then you would end up getting a classifier. You could end up getting a classifier that overfits. The regularizer just says, hold on, don't just depend on the training data, try to penalize complexity also. So regularization penalizes complexity. Is there a way to show or visualize the regularizer graphically? I don't know, to be honest. I haven't, I've thought about this question and I don't have a very good handle on that. For me, a regularizer is just more, it's, so let me give you some examples of regularizers, if, even though this is not really used. If, for example, for decision trees, a regularizer could be the depth of the tree. Larger the tree, the larger the depth, the more it tends to overfit. So you can think of the depth of a tree as a regularizer, except it doesn't really fit within this style of thinking. It fits within this thing because this is just an abstract statement of the problem. But you can't enumerate all trees because that's a combinatorial problem. So the optimization becomes hard. So regularization is it depends on the kind of classifiers that you use. So do we choose the regularizer or is it standard based on the hypothesis space you're working with? Often the regularizer is just chosen for you. So so if you're using a linear classifier, the most common regularizer is this L2 regularizer that's on the screen right now. If you use, but you know, there are other regularizers that exist. So the L1 regularizer is simply the sum of the absolute value of all the weights. So if you have D, if your weight vector has D elements, the L1 regularizer is simply the sum of the absolute value, and so on. This is just, these things exist in standard libraries. I think the next two questions are really the same question. How do we define a classifier as simple or complicated? And why does having a smaller weight improve generalization? Why does having a smaller weight make the classifier more complicated, less complicated? The way we define a classifier to be more complicated is, we have already seen a formal definition. You can think of this as the VC dimension. The VC dimension corresponds to, you can think of the regularizer as a function that correlates with the VC dimension. And that's why the squared norm regularizer makes sense. Because remember, from the theorem from Vapnik, the weight vector, so this is an answer. So to the question of the last question that was Hans, how do we define classifiers as more simple or complicated? VC dimension provides a route. And to the previous question, why does smaller weight improve regularization? That's because small norm of W gives you larger margin, and larger margin from the theorem from Vapnik gives you smaller VC dimension, and smaller VC dimension improves generalization. This is the argument that we saw when we built up the support vector machine. Cool. These are all excellent questions. I want you to kind of think about this a little more, because this is, in some sense, the standard operating procedure, at least in modern machine learning libraries. Often you will not see a regularizer explicitly showing up, because sometimes, at least in a lot of standard libraries today, instead of using regularization as part of the optimizer to penalize complexity. Something else that's called dropout is used. We'll see dropout in a few weeks. All right, I'm going to switch gears now. I'm going to move from loss minimization to a completely different topic, or at least what starts off being a completely different topic. And then in a few weeks, we'll come back to this very familiar loss minimization style problem. So I'm going to now go from this pack style thinking about learning to Bayesian learning. So we've already seen what it means. What does learning mean? This is just a checkpoint of where we are. We've seen this question. We've asked this question multiple times. What does it mean to learn? We can answer this question as using the mistake bound model, where we say that learning is when a classifier stops making mistakes. And if I can guarantee that a certain learning algorithm will only make a polynomial number of mistakes, I'm going to define that as successful learning. I can also define success using the notion of pack. So in pack learning, we talk about sample complexity and we have bounds on generalization error. And essentially in pack learning, we say, I'm going to define a learning algorithm to be successful if with high probability greater than 1 minus delta, that learning algorithm produces a classifier whose error is low. Under these models, we've seen various learning algorithms. We've seen the perceptron under the mistake bound family. We've seen SVM under the pack family. And in your homework, you will see AdaBoost, which is also kind of historically, it owes its lineage to the pack family. So, and in all these cases, we have the learning algorithm produces a classifier that that gives a label to a certain example. In today's lecture, and maybe a few lectures going ahead, we're going to look at the third approach for answering the same question: what does it mean to learn? This strategy gives us what's called Bayesian learning. There are different algorithms under this regime. We will cover logistic regression first, and then we'll move on to naive Bayes towards the end of the semester, provided time is available. So today's lecture, however, is not we're not going to talk about either of these algorithms. Instead, we're going to just look at what's Bayesian learning. And given that there are only 15 minutes left, I'm not going to talk about all of these things here. I'll just talk about what's Bayesian learning. On next Tuesday, we'll look at maximum a posteriori and maximum likelihood estimation. And then we'll work through a couple of examples of maximum likelihood estimation. So let's get started. Let's start with what is Bayesian learning. There are a few different ways to think about Bayesian learning. One way of thinking about it is the goal of learning is to find the best hypothesis from some set of hypotheses. As long as we have a clear definition of what is best, we might be able to at least operationalize this idea. In the loss minimization scheme that we just saw, we define best as the hypothesis that has the lowest empirical loss plus regularizer. Under the Bayesian scheme, we are going to define best as the classifier that is the most probable one. How do we define this most probable one? We need to assume some sort of a probability distribution over the set of hypotheses. We need to somehow identify or discover or somehow put a probability measure on top of all the set of functions in the hypothesis space. And that's what we'll be doing. In addition, we'll also need to know about some relationship between the data and the observed data and the hypothesis. And it turns out that this idea of using most probable or using the probability distribution over functions is colloquially called being Bayesian about something. And we can be Bayesian about other things also. We can be Bayesian about the parameters of the model. We can be Bayesian about the hyperparameters. Essentially, we keep asking what's the probability distribution over these things and try to find the most probable one, or try to sample from the distribution so that we get higher probability things more likely, and so on. Let's look at why this is a useful strategy. This is just another way of answering the question, what does it mean to learn? The nice thing about Bayesian learning is it gives us practical learning algorithms. A lot of learning algorithms can be seen from the perspective of Bayesian learning. For example, naive Bayes, logistic regression, and some of you may have heard of hidden Markov models, conditional random fields. A lot of these things can be thought of, and topic models, for example, can be seen from the lens of Bayesian learning. It gives a very clean, systematic method for combining prior knowledge with observed data. If I know something about the hypothesis space, if I know, for instance, that my hypothesis space should only contain functions of a certain type, or I prefer classifiers of certain with a certain property, maybe for some reason I know that my classifier should have higher weights. My linear classifier should have higher weights in the first three terms than the rest. How do I introduce this knowledge? So the Bayesian perspective gives you a systematic way to combine prior knowledge with the data that we observe. And it also gives a conceptual framework to think about learning. It gives us tools to analyze learning. So let's see how this works out. To start things off, the first thing that we need to kind of really think about, and that's most likely that'll be the thing that we'll spend most of our time, the rest of today on, is the Bayes theorem. The Bayes theorem, named after Reverend Thomas Bayes, is a rather old idea. It's a rather important idea. It's something that is worth truly internalizing. It simply says if you have P of y given x, y and x are random variables, P of y given x is simply P of x given y times P of y divided by P of x. This particular statement is misleadingly simple. But before we talk about Bayes' theorem, I'd just like to understand how many of you have encountered the Bayes theorem and the usual terms that we see with Bayesian learning before. So I'm going to launch a poll with a few questions. This is anonymous, and just feel free to answer as many. There are 4 questions. Feel free to answer as many or as few of these as you would like. So the poll is just asking if you've seen Bayes' rule before, if you've seen terms like prior distribution, posterior distribution, and likelihood before. And my usual threshold for stopping the poll is if at least 80% of you have answered, and it looks like you have. So I'm going to end the poll and just sharing the results. It seems like more of you have seen the Bayes rule, and more of you have seen likelihood than things like posterior and prior. And these are the terms that we'll be using going ahead. So let me just briefly kind of introduce the Bayes theorem and introduce you to these phrases. And we'll be using these phrases routinely going ahead. So the Bayes rule, P of y given x, blah, 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 is simply shorthand for the probability that y takes the value little y when x takes the value little x is identical to the probability that x takes the value x when y takes little y times probability of y takes the value y divided by the probability of where x takes the value x. As you can imagine, this is a really, it gets painful saying this all the time. So we will only be using this kind of notation. P of y given x equals P of x given y times P of y divided by P of x. What do these things mean though? The first thing to think about is P of y. P of that expression there is called the prior probability. Prior probability is telling us what is our belief in Y, irrespective of whether we have seen X or not. Just to remind you, what is this notation? P of something given something else is this is observed and this is unobserved. So, or that's the one that we want the distribution over, the second thing here. So in the prior distribution phase, without making any observations, what do you know about the random variable Y? What's the distribution? So for example, without actually measuring the temperature in Antarctica, what do you know about the temperature in Antarctica? I know it's cold. My prior belief about the temperature in Antarctica is cold. I don't need to take a measurement. The measurement could be X, for example. Without taking the measurement, I still know it's cold. That's the prior. The likelihood is the term that's P of X given Y. What's the likelihood of making a certain observation given that the Y takes a certain value? For example, what's the likelihood that, what's the probability of, say, the temperature in Antarctica, in the South Pole, is below freezing, knowing that it's cold, knowing that it's uncomfortably cold. So this is called the likelihood. The likelihood is what's the probability of a certain observation had the Y been something. The P of Y given X is called the posterior probability. What's the probability of Y knowing that X has been observed? So in some sense, you can think of the Bayes rule as a way of inferring what's the posterior given the likelihood in the prior. So let me walk you through this, what I mean by that. Before we make any observation, our belief on Y is P of Y. X is the observation here. Before we make any observation, our belief about Y is P of Y. And then when we make an observation, somehow, hopefully, I mean, after making an observation, hopefully our beliefs are updated. Otherwise, we're just being blind to the world. So after making the observation, how is the belief on Y changed? And the Bayes theorem says, after making an observation on X, your probability of Y, the distribution over Y, changes in proportion to what you originally believed about Y. So that's the prior, and how much X is influenced by Y. That's your likelihood, or how specifically X is influenced by Y. This is a sort of an intuitive way to understand the Bayes rule. So the Bayes rule is simply saying the posterior probability is proportional to the likelihood times the prior. This is something that we will encounter, we will be using again and again and again. Notice that I have been very, very kind of non-committal about what X and Y are. X and Y can be any random variables. X, for example, could be the temperature at this moment in Antarctica, and Y could be the random variable, the Boolean thing that decides, would I feel cold in Antarctica or not? Alternatively, X and Y could be more complicated things. X could be a collection of the examples, the event that we observe a certain data set. And Y could be a distribution or a random variable that corresponds to, I'm choosing this particular classifier as the best one. So X and Y can be, anything. The Bayes theorem does not really care about what X and Y actually are. And in fact, more importantly, the Bayes theorem was described in this form way before we had the words like classifier and hypothesis space. So Reverend Thomas Bayes could not have been inventing this for machine learning. I'm going to skip through this slide here. That's a probability refresher. This is just meant to be something that you already hopefully know, that the probability of A and B is probability of A given B times probability of B. The two variables are independent if their joint probability is the product of their probabilities, and you can marginalize out this theorem of total probability says for any event B, probability of B is the probability, the sum over all possible values that some other random variable can take. Probability of B given AI times P of AI. This is stuff hopefully that you've seen before. I don't really want to spend time on this. If you haven't seen it before, I would encourage you to go over this and kind of, or if you've forgotten this, just revisit this thing. Let's maybe in the 4 minutes that are left, I want to briefly introduce Bayesian learning and then pick it up from there in the next lecture. In Bayesian learning, we are given a data set and we want to find the best hypothesis. And the question that we need to address is what does best mean? In Bayesian learning, we use we define best to be the most probable hypothesis. More concretely, we define a hypothesis H to be good if the probability of H conditioned on the data is the highest. We want to find that classifier that's the most probable given the data set that we have. How do we interpret this? We want to find the hypothesis that maximizes P of H given D. Effectively, what this is asking is what's the probability? This is the posterior probability over the hypothesis space. The posterior probability is simply asking what's the probability that H is the hypothesis given that the data set D is observed. The main insight here is we are treating both H and D as events. D is a data set, right? However, in this particular expression, D is the event that we observed this particular data set. Among all the data sets that could exist in the universe, this particular data set is the one that we have. Then this is the data set that represents, say, the problem of spam detection. That's the event we have that we are calling D. And H is the event that among all the hypotheses that exists, this particular one is the true classifier. So in some sense, the posterior probability is asking what's the probability that this H is the true classifier, given that among all the data sets that might exist, I have seen this particular data set. So both of these are random variables. Because both of these are random variables, both of these are events in some sense. Because both of these are events, I can apply Bayes' rule. I can blindly apply Bayes' rule. P of H given D is P of D given H times P of H divided by P of D. But the fun part of this is trying to interpret what this equality means. The first term on the right is the prior probability. H is an event, right? It's the event that this particular hypothesis is chosen. The prior probability of H encodes background knowledge. It's the distribution that says, what do we expect the hypothesis to have been before we saw any data? In the absence of any information about the hypothesis space, can we say anything about a preference for one hypothesis over another in the absence of any data? If you don't have any such information, then essentially P of H could be the uniform distribution. The second term from the right is the likelihood. The likelihood is what's the probability that if H was the hypothesis that was the true one, this particular data set that you have at hand would be the one that is observed. So the likelihood is simply asking what's the likelihood of seeing this data set when a certain hypothesis, H, is the true hypothesis. So once again, of course, there's also the denominator D, which I've just ignored all the way through. It's simply saying what's the probability that this data set is observed, independent of any knowledge about a hypothesis. Since the denominator doesn't really depend on H, and we're going to maximize this expression anyway, that gets tossed out. So we'll not spend too much time on P of D. Okay, I think this is a good place to stop. I'm going to kind of revisit this once more in the next lecture. I want you to kind of go through this part of the class again before we meet on Tuesday, simply because understanding just what's on the slide right now is extremely crucial for operationalizing Bayesian learning. And this will be what we will use, for example, to define logistic regression and such things. So do go over this once again. I'll stop. We can pick up on next Tuesday There'll be a homework available sometime through the day that also asks you to go over a lecture and answer some questions. It'll be due in a week. I'll see you all on Tuesday. Thanks.